There is a state of matter that moves forever, not almost forever. Not for a very long time, forever, without consuming energy, without slowing down, without stopping. Classical physics says that is impossible. The second law of thermodynamics, one of the most fundamental rules in all of science, says that any system left to itself will eventually run down. Energy dissipates, motion stops, everything tends toward stillness. Time crystals don't. They were first theorized in 2012 by a Nobel Prize-winning physicist. The scientific community told him it was impossible. 4 years later, experimentalists proved him right. In 2021, Google confirmed them using a quantum computer. And in March 2026, 8 weeks ago, physicists at New York University created a new kind of time crystal using sound-levitated particles that breaks Newton's third law of motion. Not bends, not challenges. Breaks. For every action, there is an equal and opposite reaction. That has been the foundational rule of classical mechanics since Isaac Newton published it in 1687. It is the rule that makes every machine, every vehicle, every structure in the physical world work the way it does. The levitating time crystal doesn't follow it. This is not fringe science. This is peer-reviewed physics published in Physical Review Letters, one of the most respected journals in the field, 6 weeks ago. This is what matter can do, and we are only just beginning to understand it. To understand what a time crystal is, you first need to understand what a regular crystal is. A crystal, like the salt on your table or a diamond or a snowflake, is a material whose atoms are arranged in a repeating pattern in space. Every few nanometers, the pattern repeats. The same atoms in the same positions over and over. That spatial repetition is what gives crystals their distinctive shapes, their hardness, their optical properties. Crystals have what physicists call spatial symmetry breaking. Instead of atoms being distributed randomly, which would look the same from any direction, they lock into a repeating grid. They choose a specific arrangement. They break the symmetry of space. In 2012, Nobel laureate Frank Wilczek, one of the most celebrated theoretical physicists alive, asked a simple question. If matter can spontaneously break spatial symmetry and create repeating patterns in space, why can't it break temporal symmetry and create repeating patterns in time? A system that repeats not in space, but in time. The same configuration cycling back to itself over and over. Not because energy is being pumped into it, but because that is simply what it does at its lowest energy state. He called it a time crystal. The physics establishment was skeptical. Multiple papers were published arguing the idea was mathematically impossible. The Nobel laureate was told he was wrong. He wasn't. In 2016, 4 years after Wilczek's original proposal, 2 independent research teams simultaneously announced that they had created time crystals in the laboratory. One team used a chain of ytterbium ions, charged atoms, cooled to near absolute zero and manipulated with laser pulses. The other used nitrogen vacancy defects in diamond. Both systems showed the same behavior. When nudged out of equilibrium with a periodic pulse, like tapping a pendulum, the systems oscillated at exactly half the frequency of the input pulse. Not the same frequency. Half. The system was spontaneously choosing its own rhythm. That is the signature of a time crystal. An input at one frequency produces an output at a different frequency, the system imposing its own temporal pattern on the energy being put into it. The results were published in Nature in 2017. The physics community accepted them. Wilczek had been right. But these were exotic, fragile systems, requiring temperatures close to absolute zero, requiring isolation from any environmental interference, requiring equipment that exists in perhaps a dozen laboratories worldwide. The question became, can we build something more robust? Something stable at room temperature? Something that can actually be used? In 2021, a team of researchers from Google, Stanford, Princeton, and other institutions made an announcement that should have been front-page news everywhere. Using Google's Sycamore quantum computer, the same machine that had demonstrated quantum supremacy in 2019 by completing in 200 seconds a calculation that would take a conventional computer 10,000 years, they had created and observed a time crystal. Not in a cryogenic laboratory, not using exotic ion traps, inside a quantum computer. The Sycamore processor contains 20 qubits, quantum bits, that can be manipulated individually and collectively. The team used these qubits to simulate a chain of interacting quantum particles, applied periodic pulses, and observed the time crystal behavior. The system oscillated at half the drive frequency, consistently, stably. The result was published in Nature in November 2021. It confirmed 2 things simultaneously. First, Time crystals are real, reproducible, and observable in engineered quantum systems. Second, quantum computers are capable of simulating phases of matter that cannot be easily studied in conventional laboratory settings. This was not a theoretical curiosity anymore. This was a confirmed, reproducible phenomenon, occurring inside one of the most sophisticated machines ever built. And the implications were starting to become clear. March 22, 2026, New York University. Physicists David Greer, Mia Morrell, and Leela Elliott published a paper in Physical Review Letters describing a completely new kind of time crystal. No quantum computer, no cryogenic cooling, no exotic ions, styrofoam beads floating on sound. The setup is almost comically simple, a device approximately 1 foot tall that you can hold in your hand. Sound waves are used to levitate small beads in midair, a technique called acoustic levitation that has been known for decades. The beads float, suspended against gravity by the pressure of standing sound waves. When the beads interact, exchanging sound waves between themselves, something extraordinary happens. A larger bead scatters more sound than a smaller bead, which means a larger bead exerts a stronger force on a smaller bead than the smaller bead exerts back on the larger one. The forces are unequal. Newton's third law, for every action an equal and opposite reaction is violated. Not approximately, not at the margins, structurally. The interactions between the particles are fundamentally non-reciprocal. And because of this asymmetry, the beads begin oscillating spontaneously. They start ticking, without any energy input driving the oscillation. A steady, repeating rhythm emerging from the imbalance. A time crystal, visible to the naked eye, operating at room temperature, on a device you could put on a desk. The senior author of the paper, Professor Greer, described it this way: time crystals are fascinating, not only because of the possibilities, but because they seem so exotic and complicated. Our system is remarkable, because it's incredibly simple. A Nobel Prize-winning idea confirmed in a quantum computer, now observable in floating styrofoam beads. Here is where we need to be precise, because this is the point where popular science coverage tends to either oversimplify or sensationalize. Time crystals do not violate the second law of thermodynamics. They are not perpetual motion machines in the classical sense. They are not producing usable energy from nothing. What they are doing is something more subtle, and in some ways, more profound. Classical thermodynamics says a system at equilibrium, its lowest energy state, should be static. No motion, no change. Just stillness. Time crystals are systems whose lowest energy state involves motion. They are not fighting against thermodynamics. They are revealing that thermodynamics, as we understood it, was incomplete. The equilibrium state of a time crystal is a perpetual rhythm. It is not consuming energy to maintain that rhythm, any more than a crystal consumes energy to maintain its spatial structure. The motion is the ground state. The motion is what the system is when left alone. This is genuinely new physics, not a refinement of existing physics, not a correction of a minor error. A new category of behavior that was not in the framework. The March 2026 discovery adds another layer. By demonstrating time crystals in a system that also violates Newton's third law, the NYU team has shown that non-reciprocal interactions, forces that don't balance, can be a driver of time crystal behavior. This connects quantum physics to classical mechanics in a way that wasn't understood before. And it connects, intriguingly, to biology. The NYU paper makes a specific observation that deserves attention. The non-reciprocal interactions driving their time crystal, where one particle affects another more than it is affected in return, bear a structural resemblance to certain biochemical processes in living organisms. Specifically, circadian rhythms. The biological clock, the mechanism that tells your body when to sleep, when to wake, when to release hormones, when to feel alert, is driven by molecular oscillators. Proteins that cycle through states in a repeating rhythm. Genes that switch on and off in patterns that persist even in complete darkness, even in isolation from environmental cues. The molecular interactions driving those rhythms are, in some cases, non-reciprocal. One protein affects another more than it is affected in return. The imbalance drives the oscillation. The same physics, different substrate. The implication, which the researchers acknowledge carefully, is that time crystal dynamics may be operating inside living cells. That the rhythmic behavior of biological systems may be an instance of the same phenomenon that makes levitating styrofoam beads oscillate spontaneously. Life as a time crystal. That is not a confirmed finding. It is a direction of research. But the fact that a quantum physics paper published in 2026 is pointing toward a connection between new states of matter and the molecular basis of biological timing, that is not nothing. Beyond the theoretical implications, what can time crystals actually do? The most immediate application is quantum computing. The fundamental problem with quantum computers is decoherence. Quantum states are extraordinarily fragile. Any interaction with the environment causes them to collapse, destroying the calculation. Maintaining quantum coherence long enough to perform useful computations requires extraordinary isolation and cooling. Time crystals are stable. Their oscillations persist without energy input. Research published in October 2025 from Aalto University demonstrated that time crystals maintain coherence for orders of magnitude longer than conventional quantum states. Used as memory components in quantum computers, stable, long-lived, self-sustaining time crystals could solve the decoherence problem that is currently the primary obstacle to practical quantum computing. The second application is sensing. Time crystals are exquisitely sensitive to perturbations. Small changes in their environment cause detectable shifts in their oscillation frequency. This makes them potentially the most precise sensors ever built. GPS systems, gravitational wave detectors, medical imaging, any application requiring extreme precision in measurement. The NYU levitating time crystal, operating at room temperature on a handheld device, is specifically mentioned in the paper as a potential basis for new oscillator technology in computers, phones, and GPS systems. The physics that breaks Newton's third law may be inside your pocket within a decade. In 2012, a Nobel laureate proposed a new state of matter. The physics community said it was impossible. In 2016, 2 independent teams built one. In 2017, Nature published the results. In 2021, Google confirmed it inside a quantum computer. In 2025, researchers showed they could dramatically extend quantum coherence using them. In September 2025, physicists created the first time crystal visible to the human eye. And in March 2026, 8 weeks ago, NYU physicists created one using floating styrofoam beads that breaks Newton's third law of motion. A device 1 foot tall, holdable in your hand. A new state of matter, perpetual rhythmic motion as a ground state. Non-reciprocal forces that violate the foundational rules of classical mechanics. Potential connections to the molecular basis of biological timing. Applications in quantum computing, sensing, and communications that could reshape the next decade of technology. All of this confirmed, all of this published, all of this happening right now. And if you search for it in mainstream media, you will find almost nothing. The things that shouldn't exist are always the ones that matter most. Drop a comment. Does this change how you think about what physics is actually capable of? Because I think we are in the early stages of something that is going to rewrite the textbooks.